The construction process for this project began in class, where we both built the coil itself, utilizing the 1 meter of copper wire provided by teacher, and bending it into a circular fashion with two armatures sticking out at opposite ends. After that was completed, we took off the insulation on the armatures by scratching it with sandpaper. For one armature, only one side of the insulation was moved, whereas for the other one, all sides of the insulation were removed. From there, we built the base and stand of the motor, utilizing a block of wood as the base and manipulating and bending paper clips with pliers uh, as the stands that would hold the coil. To stabilize the paper clips, we hammered thumbtacks into the block of wood, holding the paper clips down and preventing them from wobbling at all. After that, we obtained connecting wires, battery, and from there began our initial testing.
Yeah, so we're currently trying to test this motor out. As you can see, it has some difficulty in rotating, but we do know that the current is passing through the system.
After the minimal results we were receiving with our first coil, we decided to make a new coil in which we tightened all the loops to prevent any air gaps between the loops, and we ensured that the two armatures were straight and on the same plane as compared to our previous coil. So we weren't able to achieve vastly greater results with this new coil, and we inferred that this was due to the large mass as a result of the increase in the number of loops. So we decided to take a different approach with a coil of fewer loops and lighter mass as an experiment.
We're currently at our other RPM run. As you can see, it's moving quite fast.
Yeah, and we
We'll try to time it.
we tested it with shorter wires, connecting wires, less coils.
So our basic theory was essentially reducing the resistance. So we use very less wires. As you can see, Sagar's kind of holding them down right now, but we will be replacing them with accurate electrical tape. In addition to that, just positioning the magnet as close as possible to increase the magnetic field present. In addition to that, the coil that we are currently using is not a lot of loops. It's maximum, I think, 2 or 3 loops. What we can really work on is just working on the axle alignment and ensuring that's correct. But as you can see, there's a consistent motion. And yeah, those are some of the improvements we made from our last time we filmed this, just reducing the resistance and increasing the alignment.
Here, I'll try it.
There you go, there you go. Alright, so we're currently spinning at a very fast rate of revolutions at a constant speed. This is above 1,000. You can't even see it on camera, most likely. But yeah, at this point, we're just working on our new strategy, which is essentially using sandpaper to purify the metal contact. At this point, it's very important to ensure that the contact between the metal is very secure so that the current passing through it can accurately pass without any kind of resistance that isn't required.
To improve the efficiency of the motor, we chose to minimize the distance between the coil and the magnet by creating a stand for the magnet, so that way the alignment of the paper clips would not have to be adjusted. After establishing the one working motor, we created various coils, each with a different number of loops. This was to find the right balance between the maximum force that can be applied to the coil as a result of the number of loops, as well as the minimum amount of mass for the coil. Although some of the coils did produce results, such as the one shown, none of them were able to achieve that same level of consistency and speed as the one working motor with fewer loops.
So as of now, we have another model of this motor, unveiling to you for the first time the X motor. As you can see, it's two perpendicular rotors tied to each other. And the way this helps improve the function is, in addition to creating a balanced weight, this magnet here essentially penetrates the field. I mean, this magnetic field penetrates the motor at twice the frequency as that of a single coil motor. what occurs is that we have the motor sitting here, and as it rotates, this motor in this position acts like a typical single sided motor. However, when it does rotate halfway, the force is distributed evenly on this part of the coil and the other side of the coil too, creating double the force and allowing it to rotate much more smoothly, as the field is in much more effective interaction with the rotor during one complete rotation.
The following depicts the setup of the motor on testing day. The materials that were used in this setup were one wooden base, two thumbtacks, two identical paper clips. Of the 1 meter of 18 AWG enameled copper wire that was provided, 17 centimeters was used for the actual coil, and then an additional 5 centimeters was used for the magnet stand. Along with that, two connecting wires, one AA battery, and one ceramic magnet were used for the setup of this motor.
On the day of, the single-sided rotor was performing at a rate of 2800 RPM, while the X rotor was performing at 5000 RPM, as the average between both trials. Although optimizing techniques were attempted to be implemented, such as tightening the radius of the axle holders of the paper clips or placing the magnet at an angle, significant increases in the RPM were not present. The motor had performed at a significantly higher RPM during testing at home. However, it is probable that the alignment of the paper clips may have been skewed during transportation of the apparatus to school, hindering the performance of the motor itself. When a current passes through the circuit made up of the battery, connecting wires, paperclip, and the conductive coil, the armature becomes a temporary electromagnet that generates its own force. The ceramic magnet, however, is a permanent magnet that always has two poles. This, as a result, creates a permanent magnetic force. The repulsion of the poles of the temporary electromagnet with the poles of the ceramic magnet create a force that rotates the armature by half a revolution. This is in correlation with Lorentz law, applied at a larger scale throughout the cable and exerts a force modeled by the equation F is equal to BIL sine theta, where F represents the force acting upon the armature as a result of the magnetic field B from the north to the south pole being present at an angle theta to the current flowing in the coil represented by I. At this point in the revolution, there is also present on the other side of the coil a force that is directly opposite in direction due to the current flowing in the opposite direction itself. These two forces, in tandem with the magnetic fields and current, provide the necessary conditions for rotation to occur. For the armature present in the motor, however, these forces act only up to half a revolution due to the lack of a commutator. However, as soon as the insulated portion of the axle makes contact with the paper clip, the remaining half revolution is completed by inertia and the force of gravity. This harmonious synergy between magnetic fields, forces, and current flow are the pinnacle for motor operation. Overall, this motor assignment had provided a great insight into one of the most fundamental aspects of physics applicable to real life today. Through this rudimentary version of the motor, we were able to experience on a first-hand basis the complexity in designing and constructing a technological device. The application of physics principles such as those pertaining to electricity, magnetism, and the like have developed key design, testing, and development, most of all creativity, in amalgamating physics and a little bit of hands-on involvement to create great machines.